So I wanted to create a new video. I've been wanting to create a new video for a while, and I've tried several times actually, but it's a difficult subject. Today's video is called Physics Will Never Be Solved. I'm very pessimistic here lately. Now there's many reasons to think I'm full of shit. Don't get me wrong. I could definitely be wrong. There's no doubt about that. But chances are I'm not wrong. The reason I say physics will never be solved, I don't mean that there's going to be some little bitty tiny thing that we can't figure out. That's going to be true no matter what, almost. There's always going to be some percentage of physics that we'll have to figure out how to do. It'll be complicated. Especially because there's living things. Like if you want to predict living things, then good luck with that. That's a hell of a physics problem. So of course, physics will never be solved in that case. What I mean by physics being solved is essentially this quantum gravity problem. Not just quantum gravity, but dark energy, dark matter, all of these things. The reason that physics will never solve these problems is because there's no one with enough credibility to make an impact. And I doubt there ever will be, because in order for you to get credibility, you basically have to go through this orientation that takes like 40 years of you kissing the feet of the orthodoxy. And so that's how you gain credibility. That's how you get to the top, is you basically say everyone in the orthodoxy is right about everything. And that's how you publish papers. For one, if anybody claims that they have solved it, there's no amount of math, there's no amount of talking, no one is going to listen to them. I know this because I have made this claim. I have solved physics. And I have. It wasn't difficult. The reason I made this video tonight is because I just happened to look in my comments, and there's only a handful of comments. My channel has basically collapsed because I've stopped making videos. And the reason I've stopped making videos is this exact thing. One of the comments was, yeah, this guy solved physics. Yeah, right. All these other smart people couldn't do it, but he was able to. And he published it with his AI slop on Amazon. And there's no reason for him to not comment that. Everyone should think that. When I make these videos, I'm really not talking to the average person. Sure, the average person, if they're interested in this sort of thing, they can read into it. I'm hoping to get an expert. I'm hoping to catch an expert with a hook. But it's not going to happen. It's not going to happen. No one is going to take the time to try to comprehend what I'm saying. Even though the things that I'm saying are actually the simplest things ever. Essentially, my points are... So essentially, everything that I stand by can be folded up and put into this. If you use a strict adherence to the core principles of general relativity, and by general relativity I just mean general covariance and diffeomorphism invariance, then the resulting geometry resolves almost all of the problems in cosmology, and it resolves all of the incompatibility issues with general relativity and quantum field theory, and numerous other little things in quantum field theory. But the main thing is that you have to follow A, general covariance, and B, diffeomorphism invariance. Now, these two things are essentially what creates general relativity. So, besides the definition of your manifold, general covariance is it's the idea that there is every frame that you can create, imagine with math, you know, uh, every frame of reference, every observer's point of view, every perspective that you can come up with, every region of the universe is going to follow the same physical laws. And by the follow the same physical laws, that just means all of the equations for physics are the same, no matter what in the universe. So no matter, now you can have equations that are nonlinear and that do different things, but they're still going to be, from every observer's perspective, those equations are going to be the same. Okay. And then you have diffeomorphism invariance. Now, diffeomorphism invariance is basically saying that space-time is not it's not a thing. No, that's actually not the definition of diffeomorphism invariance, but that's my definition of it, because that's essentially what it means. It means that you can't have special space-time points. In other words, you have to uh, uh you can't, if you deform your metric or your frame of reference or whatever, if you deform the manifold in some way, then the space-time points don't count towards anything. By that, I mean, if you label them, the label disappears as you morph it. So it can't really have physical meaning. I'm doing the best I can to explain this without being very precise. I mean, I'm not a physicist, and I'm definitely not a physicist worthy of talking about diffeomorphism invariance. But the idea is very, very simple. So it's your space-time points don't impact the future, if this makes sense. It's not like matter and mass. Matter and mass actually impact the future. The space-time points don't. I really hope that makes sense. Or the past, or it's not impacted by the past either. There's no energy in these things, so there is no space-time point. Like, it's just it's a human concept created to keep track of where the actual things are in relation to the other things, not in relation to space-time. And so that's the whole point of diffeomorphism invariance, is that space-time is not the reference point. Okay? You can't just have a labeling system for all the space-time points and then the mass and energy calculated that way, because the space-time points have no impact. And essentially is what this means. In geometry terms, this means that there is only one physical surface. And this is true. It means that there is only one physical surface. Now, you can have other surfaces. You can have these conceptual surfaces, and you can have surfaces within surfaces. But it's only one physical thing, only one physical surface, the entire universe. And these are my definitions of general covariance and diffeomorphism invariance. Now, I'm not suggesting we change the definitions to mine. I'm saying that we need a strict adherence to the actual definitions, not to my definitions, to the actual definitions, mathematically. And when you do that, it turns out it's very difficult to create a metric solution, for one. And so there's a lot of problems that get solved when you do this. Now this is actually not where I started. This is not where I began, but this is where I've ended up because I think this is the best way to explain it. For one, lambda CDM violates both general covariance and diffeomorphism invariance. Now, they will argue that it does not, but it does. For one, it violates general covariance because there is a preferred slice. Okay, this preferred slicing requires you to label it. See, in lambda cosmology, lambda CDM, this is the mainstream cosmology. They believe that the universe is homogeneous and isotropic. They need it to be homogeneous and isotropic because the solution, in order to create a solution to the field equations, you need a lot of symmetry, and it just makes it easier. Otherwise, it's extremely difficult because you have all these nonlinear differential equations that you got to solve, and it's difficult. And so if you add a bunch of symmetry, things like it's homogeneous. In other words, it has the same average mass density everywhere. When they say things like that, they're violating general covariance. How are they violating general covariance? Because they're creating a preferred slice. And by a slice, I just mean it's a radial slice. So if you have a metric solution, a slice would just be one measurement on R. And it would basically include in an infinite direction everywhere, but just along that plane. And so the average mass density would be the same for that plane. However, there's been a few people that have demonstrated that you can't stitch these slices together. And the reason you can't is because mass density is inversely proportional. Well, in our universe it is, but mass density is solved by rho equals mass divided by volume. And so in our universe, this ends up meaning that mass density is inversely proportional to the volume. Now, Einstein actually spoke about this in his or one of his early articles, Cosmological Considerations, where he talks about there's the mass density tends towards zero as you approach infinity. And so this is a problem. That's why he proposed using homogeneity. But Einstein's solution of using homogeneity is actually wrong. It creates what's called an ansatz. I don't know how you say it. I think it's ANSATZ. Ansatz. It's a way of describing your symmetry. It's a way of formulating your symmetry. And so Einstein suggested homogeneity. It does not work, but it's still around. We're still using it. The FLRW metric, which is what lambda cosmology uses, the FLRW metric solution violates. That's what is violating general covariance and diffeomorphism invariance, but it's not actually a metric solution. the FLRW metric is not, like, they call it the metric, but it's not really a metric solution. It's more of a nonsense. That's the whole point of me bringing it up. It's just a way of formulating your slice. And so I had a quick conversation. I paused the recording and had a conversation with ChatGPT here. And I started off by saying that I asked it to define general covariance, and I wrote lambda CDM here, and I meant FLRW. I should have said the FLRW violates general covariance, but regardless, it says obviously no, it does not. And then I got it to play around with a couple concepts, but I finally ended up just saying rho equals mass divided by volume, and it immediately responded with, I see the point you're aiming at. And that's because when you are using an expanding metric, if you're using homogeneity, then mass does not equal, or rho does not equal mass divided by volume. That's not how you find mass density. Mass density is no longer equal to mass divided by volume in the FLRW metric. And so this entire concept of expanding space-time violates both principles. The reason it does is because these space-time points are what's pushing things apart. And so that's why they're having a hard time. That's why they're having a hard time quantifying gravity. That's why they're having a hard time predicting the vacuum energy density. That's why they're having a hard time with dark energy, dark matter. I can show all of this. The math is not the hard part. It's having a captive audience is the hard part. Like a captive audience isn't the right word, but I wish I could have a captive audience. If I had people that I absolutely had to be able to force this information into their brain. If I could do this, like to just a handful of experts, say, that have loud voices, if you locked me into an elevator with Sean Carroll, I promise I would bet everything that I could change his mind. Now, that might be a giant mistake, but I could at least get him to a point to where he would want to investigate it a little further. So just stick with me. This story gets thicker. Okay, there's plenty of meat to go around, but you have to stick with me. I want you to agree with everything I've said so far. Now, you may not agree that the FLRW metric violates general covariance. That's fine. But mass, the average mass density, rho, equals mass divided by volume. And so I don't know how you can change that and have expanding space. I don't know, and not violate general covariance, because it means that your mass density is decreasing with time, is what it means. You're adding a temporal element to mass density. And so that's why it violates general covariance. There's other reasons, though. There's the preferred foliation. And so it says, I responded with, like, it went all through this and talked about one slice. And so that's basically that's how they justify this. They say, yes, but if you just have one slice, then it's accurate. And we can say that slice is, say, the observable universe, and it works for these types of whatevers. The math kind of works that way. But you can't stitch the slices together. That was my next point. And it immediately responds with, right, that is the stronger point. You can't sew them together. These slices don't align. So you can't build a complete universe this way. And so my point is that's why it violates diffeomorphism invariance. And it goes back and disagrees. No, it's got all this stuff. So it's got, like, it said it would establish if there's this, and it's like it really squirms. I responded with seeing with page curves with blinders on. That's the name of an article. Um, and it actually didn't recognize it as the name of the article. It just recognized the concept. Uh, and so it responds with foliation dependent cosmological quantities, 4D invariant observables. So you can't get the 4D you can't get 4D invariant observables out of this, out of the foliation dependent cosmological quantities. But that's not what I'm saying. It's putting words into my mouth. And I told it to read the article, and then it reads the article, and it's like, yes, you're right. This is basically what the article is exactly explaining, is that these... I don't want to get into this. I'm not equipped to talk about this mathematically. I'm terrible when I start talking math. Like, I have the way I think about things and what I can do and all this, but I'm not a guy that can explain this. But regardless, this is my point: is that the FLRW violates general covariance and diffeomorphism invariance. I want you on this same page. And the answer is that yes. Like, if you're a Harvard professor teaching cosmology and you got married at an expanding universe themed wedding, and you have the words Big Bang tattooed on your shoulder, I don't care. You still have to agree with this part, because the FLRW metric is not really a metric solution. It's an ensemble. It's how you would, it's your symmetry choices that you would use for your metric solution. And you have to agree with that. And then we can move on. And so if you're not there, then I need you to get there somehow. Because even ChatGPT agrees. It's an ensemble before it is a solution. You assume spatial homogeneity and isotropy and write out the most general metric compatible with those symmetries. Okay? And so it's basically useless. It's essentially useless. Now, you don't have to agree with that part. Is a symmetry ensemble whose particular dynamical realizations are general relativity solutions. Sure, you can use it to make a solution. I don't know why I said start writing. I think that was a bubble. That was a bubble. You know what I'm saying? A autofill thing that they, whatever. So how do you fix this? Well, the great thing is that you can fix it and prove it at the same time. Not really prove it, but kind of validate it and invalidate the other at the same time. And this is something that it really makes my case so super strong. People don't understand how strong the case I have is. That is one of the things that keeps me going, is that I have one of the strongest cases in the history of physics. And it was very super simple. It's very super simple. That's what's amazing. But it is a very strong case. Let me just show you exactly how we fix the homogeneity problem. See, there's an epiphany that I had not long ago. One physical surface means one surface density. This is just the math. See, one of the problems in physics is that they have this problem. This is a problem in cosmology, in gravitational physics, in astronomy, and geometry. All of these physics related fields has this in it, and it is a problem. And this is one of the problems that I struggled with for a little while because I didn't understand what they were talking about. Uh, but there's a difference in what, like, they subscribe to something called an enclosed mass. I'm trying to find where I had this part of the discussion. Sorry. I know everybody loves watching somebody have a conversation with ChatGPT, but I said there is no such thing as an enclosed mass because that was one of its retorts about my definition of mass density. And it was like, oh, you're talking like mass density is the enclosed mass, and then this you have to integrate and all this stuff, and that's not what I'm talking about. There is no such thing as an enclosed mass. Like there is in some sense, some form. Like you're talking about the amount of mass enclosed around the sun, then you can kind of ascribe a value to that. But that's not real. Because the sun is part of the galaxy. Like, so like, you're not changing scales here. That's why my definition of mass density is just the same. It's always rho equals mass divided by volume. And when I said there is no such thing as an enclosed mass, I like it understood me. ChatGPT is amazing, especially this new one, and I've got the ultra high version too. Like I can turn this MF for all the way up if I need to. But for most of this stuff, you don't really. It's kind of a waste because you can run out pretty quick. Because sometimes it just don't stop. Now, some of you may think that it's just AI slop, and that's fine if you think that, but AI is really good. Like I'm not one of these. I despise it. I hate that we have to use this tool. But I don't. I wish we didn't have to drive cars. I mean, I'd rather ride a damn horse. I'd rather walk, but riding a horse would be pretty cool too. But like, I don't like cars. I don't like. I like air conditioning, and I like hot showers. But other than that, I don't much like any technology. But we got to use this shit. I mean, some people complained about people using computers, I guess, when they come out. And the same thing with LLMs, but they're amazing, dude. Now, they make mistakes, but as far as with math goes, man, they hardly ever make a mistake with math. And that's basically everything I'm doing is math. Okay, so let's continue. So essentially, what I am suggesting is that we use a rigid definition of mass density, and it even come up with my. Well, no, I gave it to it. I gave it I gave my version, my short formulation of surface density in here. And it's saying here, while your premise is precisely that the fundamental scaling is areal, not enclosed volume based. The enclosed volume based is not real. We want areal. But this right here, this is my latest thought, my latest formulation. And this is, I mean, my latest as in this was like 2 years ago. But this was like a major epiphany on this road is that uh, both both general covariance and diffeomorphism and variance force us to have a constant surface density. I know people don't, like, even experts might disagree with that, and I submitted an article to a contest, and I didn't win, but I discussed this, and I don't know if they just thought I was full of shit or what, but I think that this is a hell of an argument. The reason you have to have a constant surface density is because just it's like a law of geometry. If you're going to have uh, something called an average mass density or a mean mass density, if you're going to have this volumetric way of measuring mass and with general relativity, now you can have little sections of the universe that aren't a constant surface density. Like, that's not the idea here. The idea here is that it's kind of a hard leap for people to grasp, even somebody that's an expert in geometry. So I'm going to pause for another second here and try to think of the exact right wording. Okay, so general covariance tells us that the forms of physical equations stay the same in every coordinate choice, I think is a good way to explain it. And so that means surface density and surface area the form stays the same in all coordinate choices. Okay? You can't use expansion anymore. Well, ignore that. These are inevitable. 1 over r is inevitable. Why? It's because even if you use your preferred foliation, your preferred slice in the FLRW, you're going to get a constant surface density because there's only one surface. That's the whole point of general relativity, of diffeomorphism invariance. There's one physical surface, and so there's a value that you can assign to surface density. Now, this lower surface density is not a typical physical equation, really, but it is a thing. It is a thing because mass density is a thing. Because volume and mass are a thing. Because mass is a thing. Because you have mass and the way that mass is distributed in our universe, the way that physics works, then you have something called mass density. And because you have something called mass density, you have something called surface density. These are all logical equations that come straight from very simple equations. And they're all derivable and formulatable. Like, all this shit is real, is what I'm trying to convince you. Now, there may be some experts out there that are not going to be on board with this for a second, and that's fine. You'll have to read some articles. And look, I'm totally self-aware of how I sound. I know that this is absurd, and I sound absurd. Doesn't matter, I'm right, and so I'm obligated to share. And I know that sounds absurd, but it's true. I know that my voice sounds awful. I hate it. That's why this is so difficult for me. That's why I barely ever make videos. You should see my face. It'd make it so much worse. I could show my face. So be really nice with the comments, or I'll start making videos with my face on them, okay? Regardless, this constant surface density results in a distribution of matter that is proportional to 1 over r. Now, you don't believe me? I promise you this is true. And it's going to be true in the FLRW metric too, because in the FLRW metric, your chosen slice is going to have something. Now, you can have... So I fed ChatGPT I've got a project with it. It has like 40 articles on it. And so I've got, like, this one right here, I didn't give it as much. Yeah, like, it still has some of the context in this project, but regardless, it has basically 10 years worth of my work and my opinions and stuff that I've not even shared with the public. But It has all of my thoughts on this stuff, and all of these formulations and my latest grand formulations. These Hold on one second. See, I've got that. My puppy is just making noises. That's why I have to pause every now and then and do something. And she like dropped a ball behind the bed. So hold on. All right. So at the beginning of this conversation, I ask it to put together the most parsimonious disagreement between my model and mainstream cosmology. Wow. She went outside until I started talking. And then when I started talking, she came inside. I'm sorry. You're just going to have to deal with the puppy. And you're going to have to deal with my cat. And Hank probably won't make any noise. He knows what I'm doing. Hank is the most perfect dog in the world. Hank literally does everything you say. Hank's probably sitting here taking notes, honestly. Hank might be rolling his eyes and being like, no, I can't believe he said that. That's how bad Hank is. Like, Hank is more intelligent than you are. Anyways, so the disagreement is that you can't violate general covariance and diffeomorphism invariance. I have a literal interpretation of them. Some people would call it radical. I call it literal, like the law, as in you can't violate it. Now, you can create solutions to the field equations that violate it, and these are legitimate things for doing stuff, but it's not real physics. If that makes sense. It's just like you can use Newtonian physics to do stuff and it works. And you can say that that's legitimate, I guess. But in my eyes, it's not real physics. Like, I don't know how to explain it. ChatGPT does it pretty good. What did it say? Your objection. Okay, yeah. It doesn't matter. I'm not going to try to. I'm going to try to avoid referring to ChatGPT, but it's really good authority and validator for this sort of thing, because it's difficult to convince that you're right. And all I have to, it's actually pretty easy for me on this stuff. It's the because I know exactly the pinpoint now. But ChatGPT has helped me pinpoint this exact location. And the problem is that there's these God's eye constructions. Basically, you're creating a solution that violates diffeomorphism invariance or general covariance in some way. Either there's this preferred slice foliation, there's this preferred reference frame, you have a unrealistic symmetry. There's something that ain't right. And so you're shorting the algebra is what it's called. Basically, in other words, you can't stitch the whole universe together. But if you have a literal interpretation, then this the surface density is going to be a constant. And so that's why I have this. I created this. I think I've already showed this actually. Because this is general covariance, you have to have these equations have to be the same in all coordinate choices. And so this, if you do that, then you have this. This is your distribution of mass. It's inevitable. In other words, it happens in basically any cosmological solution that's doesn't violate general covariance or diffeomorphism invariance. Now, why is that important? Because this is exactly how you get to Hubble's law. And the CMB, this is everything. This is everything. And when I say everything, I mean everything. The metric solution, very simple. You have a horizon. The horizon comes from the gravitational redshift. The gravitational redshift comes from the distribution. I'll explain more. Maybe I don't need to explain. It's fucking math. So you you have each of these columns. The first one shows you how do you get the Hubble redshift. Now, Hubble's law is not really the Hubble constant is not really anything. Like, it's not real. It's like there's a redshift, but it's not a Hubble constant. Like, it's the Hubble constant is in this absurd unit. It's like seconds. Like, it reduces to seconds. So it's like not, it doesn't make sense. And so the reason it doesn't make sense is because you have to have these two regimes. And so that's why there's this two in here. And sometimes you see it's like C divided by 2 times the Hubble constant. That's your horizon radius. But really, it just depends on what you're talking about. You got two regimes there because, like, it's not a real, like, Z is nonlinear. Gravitational redshift is nonlinear. And actually, the redshift in cosmology is nonlinear. That's why there's dark energy. And so, when you resolve the redshift, you also resolve dark energy. Bam, it just happens. It's instantaneous because it's gravitational redshift. So it knocks out expansion and acceleration at the same time. And it's still 1 over r. This is 1 over r. It perfectly aligns with Hubble's law. At that, it depends, like the Hubble constant, like I could say this 72 kilometers per second or whatever. But it's Z. That's really what it is, okay? But it still matches, and I'll show you how it matches because we have the cosmic microwave background radiation. The CMB is Hawking radiation with this. It's because you have a horizon. So anytime you have a horizon, it's a Schwarzschild limit, and anytime there's a Schwarzschild limit, you have Hawking radiation. Like, the physics is already there. The equation general covariance tells us that the forms of physical equations stay the same. So that's this column over here, right? Is that what that says? It's the one with temperature and all the reduced Planck's constant, all the H bars, And so I'm going to give you in the description below. You can copy. I'm going to give you some latex that you can copy and paste into Claude or ChatGPT, and so this will help you see that this formulation, all of this follows from 1 over r. Now, that's not how I got there. This is not how I arrived there. Let me explain to you the story of how I arrived to all of this. See, ChatGPT has helped tremendously with me formulating this. However, I essentially had the same shit going in 2017 with my AI slop on Amazon that I wrote. And like I said, 2017 is a book. And none of the shit that I write is AI slop. I don't care what anybody says. Like, it's really offensive to call my stuff AI slop because I spend so much damn time on it. Yeah, I use AI, especially because most of the stuff you got to use latex, and LLMs are just spit latex out like instantly. Whereas back in 2017, it would take you an hour to do one equation. Like, it's just absurd. Like, latex is a bitch. Screw latex. And so with ChatGPT, you can use it for that. Hey, and also it's great for editing and whatnot. But all of these ideas are mine. Like, literally mine. This cosmic microwave background as the Hawking radiation. In 2017, I called it the Unruh effect. I called it the Unruh effect. I thought it was the Unruh effect, and it essentially is Unruh. It essentially is Unruh radiation. Like, they're essentially the same thing. This basically, is the unification of the Unruh effect and Hawking radiation using Mach's principle. Now that's beyond the scope of this video, and I'm making claims that are outside the scope of this video. But this is the formulation of the model, and all of this comes from the metric, which is 1 over r, with a horizon. Okay? That's essentially it. This is an observer-dependent horizon. This would be the global solution. In other words, all other solutions would be a subset within this. It's because this is the only solution that does not violate general covariance and diffeomorphism invariance. And it forces this Hubble's law. It locks all of this stuff into place. So you have a single, it's not even a single parameter. You have to start somewhere. So it is a single parameter. But like nothing is adjustable. Everything is fixed in place by the geometry to the Planck scale. Like we only get the observed 2.725 with a, like, let me show you a chart. I've got a chart right here somewhere. But we only get that observed temperature if we formulate correctly and choose the right Hubble constant along with the right horizon and the right offset. Now this is in Planck lengths. And so if you're using with the Hubble constant, see, like the Hubble constant makes everything confusing because you have to have a definition for your horizon. And so here's a table here. Like it tells you, like, so if you go below that, the temperature, the offset, it changes. And because you're keeping the temperature at 2.725 Kelvin. And so it's around 2 Planck lengths is the right choice. And because it's somewhere around this 67. So everything's locked into place. So it just depends on measurements, observations. And it would be interesting where this offset is, because this offset here is how we unify general relativity with quantum field theory, because there's no other physical prediction that predicts anything smaller than this. This is me making a prediction about the location of the emission of the CMB, which is highly dependent upon the geometry, which is highly dependent upon the observed temperature. So I've got another chart here. I actually don't know if all of these are accurate or not. So this one right here is different. See, this is why I don't like using the Hubble constant, because it can confuse you. But you have to, in order for it to be, either way, you kind of get the idea. I don't even know which one of these is accurate, because it depends on your starting definition, and some of these aren't right. But let me just ask ChatGPT. We'll just stay live, because I'm trying to wrap it up on this recording right here. And so if you just stay with me for a second, I can figure out which one of these tables I generated is accurate. I thought there was only one. I thought I deleted the others, and I guess something happened. I don't even remember. And it's just so much easier because I have done this shit so much, and I've had so many different minor little tweaks. Everything is minor, but it changes. And I've recently adjusted my formulation of the metric solution. So there's just better ways of doing it that allows for something called optical closure. And so I can obtain optical closure with this and gravitational lensing. That's what the angular diameter distance is. So people have asked me that several times before, how I explain angular diameter distance, and that's with this Oh, I don't want to get into that yet. That's with this right here, this column. It's gravitational lensing, and both Benny has an article. Professor Benny in the UK. I think he's at Cambridge. He's a professor there. Uh, and Wald, who is like probably the most authoritative voice in general relativity. Period. Um, he wrote the book on general relativity. I mean, Einstein wrote the original, but Wald as basically he's basically formulated all opinions in general relativity, and he wrote uh, an article. He has a published article on. It's something like angular diameter distance in an inhomogeneous universe, which this would be an inhomogeneous universe. It's because homogeneity is impossible. Now, it's inhomogeneous is actually the wrong word to describe it too. I don't like that's not mass density is scale dependent. And so you have to stick with this. If you followed a general covariance, diffeomorphism, invariance literally, then you end up you have to. So the first top table. So with the tell me it's the one with 6. That's what I thought. I thought it was 6 because see I used to say that it was the 1.28, but no, it's actually 6. But it also like it depends. Like the meter is not like these are. It gets confusing. I don't want to dive too deep into this, but a lot of this is just bookkeeping. Okay, there's a horizon, and it just depends on how you want to formulate your like keep up with your numbers. But this is like if you're using the Hubble constant, then you have to have two regimes, and it just depends on your definition of the meter. Then, if you just use gravitational redshift z and work backwards, then this is what you get, this 6.4. So your definition of the meter is observer dependent. And then your 72 is just what you can get off of that. If you just if you just force the conversion to Hubble constant, it's actually not the exact same units, but you can do it. And then your offset is 4.305. Man, I sound a little confusing, but if you know what I'm talking about here, then this should make total sense. I hate recording podcasts because like anytime I do this, I just get tired while I'm talking because talking to a microphone and computer, you don't get the facial expressions. You don't know if they're following. Some people are following me and some people aren't. It's everything takes hold while you're doing this stuff, and it's just exhausting because my brain is having to keep track of everything, and I know I'm sounding like shit. So I'm just gonna keep trucking on. How about that? We're gonna get to my story of how I arrived here. This is the way I started because I did not think that the universe was expanding. Okay. So, as a scientific inquiry, I figured out, I read about gravitational redshift and I tried to find everything I could find out about gravitational redshift. In that initial investigation, I learned how to calculate gravitational redshift for a star. Okay. For say the sun. And then I did for Earth, I did a couple examples. And then I did a galaxy. I did like the Milky Way galaxy. Then I wanted to see how much gravitational redshift there would be for a star that's 1 megaparsec from us. So I had to figure out how many galaxies there were in a megaparsec. There's a lot. I don't know the number, but let's say there's probably more than 100,000. It's probably something like 10 to 50,000. It depends on the size of your galaxy, obviously. But just on average, it's thousands. I don't think it's millions. It's thousands, and I don't even think it's hundreds of thousands. I think it's tens of thousands, something like that. And for that, if you then calculate the amount of mass that is for that, and then use 1 megaparsec as your radius, then it actually matches Hubble's law. If you do it for 2 megaparsecs and 3 megaparsecs and 4 megaparsecs, if you keep extending it out, it still aligns with Hubble's law. And so it took me a long time to understand why physicists did not know this. And the reason they don't know this is because they use the FLRW metric, which assumes the universe is homogeneous. So there is no gravitational redshift. But this is not true. Light from a star when it leaves the star, it immediately is climbing uphill, losing frequency for any observer. Now you can find an observer. Let me close these, and then we'll get to the beginning. So let's imagine an observer that's in between galaxies. He's not close to a black hole. He's not close to a planet. He's in a little bitty tiny spaceship. He's even outside the spaceship, you can say. He's just floating in space. And he's, he's as far, he got as far away from all galaxies as he could. He used his spaceship to move him away from all light. And so he's basically in the darkest place he can get to. He's a long ways away from any galaxies. He's in between the galaxies. He can still see galaxies everywhere. For him, there's galaxies everywhere still, but they're not nearby. It's like he's just looking at the night sky and he doesn't have a home galaxy. Now, a star an atom, stars are made of atoms, correct? And the atoms are what produce the light, correct? So with your view of gravitational redshift, how does a star produce gravitational redshift at all with the mainstream view? Because otherwise you could just say it's the atom, and then you could just use the properties of the atom to find the gravitational redshift, and the atom is actually less massive and has a lower gravitational potential than him, so it'd be a blue shift. But stars have a gravitational redshift because the mass accumulates. And so the gravitational as light is leaving the star, and goes to the observer, it's gravitationally redshifted. Now, if he's looking at a galaxy, which all stars are in a galaxy, then there's more gravitational redshift. Okay? Now here's the next leap. What do I mean by this? You're looking at a more distant galaxy. Okay, so in this situation, this is the closest galaxy to him. And then if you look behind it, you can see more galaxies. And so this has a more gravitational redshift because he's still in between galaxies. So at each step of the way, there's a higher gravitational redshift. Guess what? You look further away. If he looks at some galaxies that are like several megaparsecs, there's going to be more gravitational redshift. It's because he's looking deeper into the gravitational well. Now, if you're an expert, this is helpful for people that don't have a strong understanding of metric solutions and general relativity and things like that, but maybe they've read several books, and they know how general relativity works, and they know what lambda cosmology and the Hubble redshift, and how they know gravitational redshift. They may even know how to do gravitational redshift. This is still helpful to that. But if you really want to know the expert thing, then here's my metric. And that's what this is. That's what this demonstrates. Okay, that's what the math is for. Here's this one, it's centered. That's better. Here's my metric right here. Okay, that's what this is. That's what this is. That's how this works. Now, mainstream cosmology, they say there's zero gravitational redshift. But there has to be gravitational redshift because general relativity. So why do I say that I've solved physics? Well, because this allows us to quantify, it's not quantify, that's not the right word. This allows us to cut off the energy scales. So quantum field theory has a hard time with general relativity because if you incorporate general relativity into quantum field theory, then it creates these infinite divergences. And that's because of what they're using for vacuum energy density is not scale dependent. First of all, it has to be scale dependent. And then because it's scale dependent, what are the scales? Well, the lowest possible scale is this emission offset. I've already closed them all, haven't I? Yeah, it's the emission offset from, right here. It's this right here. This is our lowest energy scale. Or this is the highest energy scale, actually. I get them reversed all the time because it's so short. It's a small 4.3 Planck lengths. This is the highest, this is the cutoff for the highest energy scale. The horizon is the cutoff for the lowest energy scale. And so you no longer have infinite divergences. You can calculate all of the different modes. Like it's quantifiable. Now it's not quantum gravity because it's general relativity. General relativity is relational. So all you have to do is get rid of the substantivalist nonsense of quantum gravity and 0 point energy and dark energy and inflation and expansion. All you have to do is get rid of all that stuff that is outside of general relativity and just use literal general relativity, and you have energy scale cutoffs that perfectly align with observations. So that's why I'm still making these videos, because I made one thing. What is that one thing? One proposal, I guess, is what you call it. The one proposal is you follow. Where is it at? Did I have it? I started the video off with it. Man, these are all terrible. Come on. It's just literal AI slop. That's what that guy said. Equations. I don't know. I think it's okay to let ChatGPT help you do equations and write, because like everything that I've put out with AI, I've spent like hours and hours and hours and hours and hours on it. And yeah, sure, it helps me, right? For sure. I'll be like, hey, can we reword this? And then sometimes, like, I want to, have my own voice. And so I will go on a hike and I will dictate. And then I will put that into ChatGPT and I'll be like, let's make some paragraphs out of this. Like, these are the ideas I want to discuss. And then it puts out something and I'm like, okay. And then I copy and paste that into another thing and I'm like, let's break this into 4 different sections and let's start writing from the beginning. And then I'll rewrite each section myself. And then it'll be like, I think you should use this word. And I'll be like, yeah. But you know what? None of that really matters because the shit I'm writing here, this physics shit, there's very little writing. Look at this. Like, this is what an article looks like. This is the latest working article. Like, it's all math. So it's like, does it really matter if we call it tangential pressure or positive? I mean, does it really matter who writes the words? No, it doesn't, because like you're trying to be, it's like law. It's like writing law. Like you're trying to create as little ambiguity as possible. You're being very deliberate with your language. And the damn language bot is better than I am at that. Now, I understand humans better, and so I have lots of edits I always want to make because I know that some of that shit sounds retarded, and some people won't know what it means, and you know, like I want, like sometimes it doesn't like the way I phrase things, and I actually want to phrase it like that. And so there's definitely the human touch that you should put on stuff. You can't just copy and paste what it what it outputs. That's for sure, because it sounds awful most of the time. Like, it's so stupid. But these days they watermark it, so there's no sense in even using the damn things. You can't even use it to put latex. Like, what happens if you just copy your own article you spent the last 6 years writing it, and you're like, I need to convert this to latex, so you copy and paste it into ChatGPT, and then it gives you latex, but then it watermarks your shit. And so now everybody runs it through a scanner. It says, yeah, it's from an LLM. Even though you just spent 6 years and it spent 14 seconds putting it in latex for you, and now it's watermarked. I don't know if it could do that or not. That's pretty intense, watermarking with latex. But and I know that some people call it latex. I've just called it latex for my entire life because that's the way it reads. That's what, so I don't care if you call it latex, that's fine. You say mater, I say mater. You know what I mean? Anyways, uh it's all equations. That's what all of this shit is. It's equations. So I don't know how I change it. The only thing ChatGPT does is add more equations. Like, I give it a starting equation or a few equations, and I'm like, how about this? And it's like, oh, we need to do this, 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 and 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 this. And I'm like, man, I don't like that. Like, I don't like, see, there's a lot of repetition with ChatGPT, but I get it. Like, that's probably how it should go. Like, I skip steps all the time. I skip shit all the time. And people would never be, like, I don't even know what this symbol, how do you say this symbol? The 3 lines? Define the limiting mass by, so I don't know what that is. And so ChatGPT helps with stuff like this. This is my damn distribution here, this 2 pi k. Like, it took me a whole year, 2 pi kr, to do this. And like, I done that on the whiteboard in my bathroom when I worked that out. So, and that was before ChatGPT even existed. So you can't tell me that my shit's AI slop, because like, I'm using it and it makes it better. But I did this shit way back. Like, you can go back, man. My damn videos are there. Like, I got a history. Like I say, my book was published on Amazon in 2017, and I called the damn CMB unruh radiation. Like, and I had the equation for that. And, I attached this Mond constant. Like unruh radiation, Mond constant. Wow, you got dark matter and the CMB right there. And so that's what all this shit is. Now I'm going to paste this formulation. I don't know if I'll be able to give you the whole article. Maybe. I don't even know if this article is ready or not. This was just like, I definitely want to choose more stuff. Like, but I'm just saying, I don't care about publishing in mainstream science. And, it's because there's no way that anybody is ever going to believe anything I say, or anyone else for that matter. Physics will never be solved, people. Physics will never be solved because people are too lazy. See, all this shit's checkable. Like, everything I've said is checkable. And so it's what I provided to you. Was I said all you have to do is follow a strict adherence to the core postulates of general relativity, namely general covariance and diffeomorphism invariance. If you do that, you have to have a constant surface density. If you have a constant surface density, you have a 1 over R distribution. A 1 over R distribution perfectly aligns with the Hubble's law. And then it produces the 2.725 degrees Kelvin in the CMB at an emission offset of around 4 Planck lengths, providing both a lower and upper energy scale cutoff. So I don't know. All I said to do was follow the core postulates of general relativity. And look, you can say all of those don't lead to the other. Fine, but 1 over R does. 1 over R does this. 1 over R does this. And you know what's amazing? Well, it's impossible to do 1 over R squared. It's impossible to do 1 over R cubed. It's impossible to do less than 1 over R. You have to have a proportional distribution to 1 over R. And that's this. This is your metric. You have to have this metric. This is the only way that you can have complete algebra. What's amazing is that if you do this, then you can also have perfect holography at all scales. So a constant surface density, 1 over R, not only gives you Hubble's law and 2.725 degree Hawking radiation temperature, and angular diameter distance, perfect optical closure with the angular diameter distance. But you also have perfect holography at all scales. In other words, the Bekenstein-Hawking entropy equation, you just put in R. You get the modes. It's scale. Everything's on the surface. All the information is on every surface. It's perfect. But nobody will ever believe me because they're too lazy to check. They think I'm arrogant. They'll call me arrogant. You can call me arrogant. That's fine. I'm not arrogant. This shit was easy. I told you, this is how I figured it out. And this is literally, I drew pictures like this in the book I had in 2017. It's because I knew this is how gravitational redshift had to work. It has to work like that. Other than that, it just doesn't work. I don't know what else to say. Like, this just makes sense. Expanding space does not. Expanding space means you have to have all this new shit you have to add, and then everything starts falling apart on you. You know why? Because it's damn opposite of gravity. That's why. Now, look, I've got videos on why the universe doesn't collapse. I've got all kinds of stuff. I'm going to end this video now. You can go back and watch the other stuff, but please note that every time I formulate, I make an improvement. And so that's one of the biggest hindrances I have is the things I've done in the past. My formulations weren't accurate back then. And so it seems to people that my credibility takes a hit. But if you actually understand all of this and give me a little leeway, you can see that my formulations have only improved. It's the exact same thing over time. And so now my formulations are perfect because it's ChatGPT has helped. ChatGPT's like, oh, like it's not really perfect because the language doesn't quite yet exist in modern physics. It's always got some sort of nitpicky thing to say that I have to point out, and it's usually wrong. The nitpicky thing is usually wrong. It'll be like, oh, now that but anyways, regardless, it's in the description. You can spend some time with it. But you got to understand that this shit is new. That I'm not a fucking genius at all. Like I'm a literal idiot. But that there is a mathematical chain. Like, I don't want you to think that I'm right because that I'm a real smart guy and that I have lots of credibility. I want you to ignore all of that and just focus on the math and the physics. That's what I want you to do. That's my point. I'm not trying. You can't trust me, bro, on this. Like, you can if you're just too lazy, I guess. But you have to actually spend some time with it. And by that I mean, like, ChatGPT is great, but you really need like good thinking. You don't want to use the free version. I mean, you can probably. It's probably okay, but it's going to disagree with me on everything. uh but you want to use a powerful LLM. I never use free versions anymore, and I haven't used Claude in a while. I haven't used Fable at all, so you can use Fable maybe. But the what you're looking for is consistency. Now, there's a little bit of disconnect maybe with this constant surface density, but to me, it just all fits in place like a damn. I don't know. I'm rambling at this point. Good night.